Welcome to AP Calculus. We're using a curriculum by Mark Sparks, available for free on Teachers Pay Teachers, and I very much appreciate him making this resource available. We're starting our exploration of calculus with limits. Calculus has three main concepts: limits, derivatives, and integrals. And limits are the foundation for both derivatives and integrals. With limits, we're going to start by looking at what does a limit mean? What's the whole purpose of it, both numerically and graphically? This is part A of this lesson. Point B will be posted later as well. And in this part, we're going to we're really going to cover for the first time the numerical and graphical approach to limits. And a couple of things to look at this particular function that we see graphed here. This function, some things that you may have learned in a previous math course, is that we can connect this function to this graph in several ways. We know that the coefficients of our highest powered terms in the numerator and denominator give us our horizontal asymptote, which we see here at y equals 2. I can also factor this to 2x minus 1 times x plus 3 over x plus 3 over x minus 3. And something else I'll notice here is that I have this x plus 3 in the numerator and this x plus 3 in the denominator. And when I have the same factor in the numerator and the denominator, I could cancel this out to make an essentially equivalent function. And that means that at x equals negative 3, this would be a discontinuity. It is a discontinuity because if x equaled negative 3, then I would have negative 3 plus 3 is 0. 0 times anything is 0, and I would have 0 in the denominator. So I see this point discontinuity here at x equals negative 3. I can find what the y value at that point in the graph is if I were to evaluate the resulting function for negative 3. So when I take out x equals 3 and evaluate at negative 3, I would get 7/6, which is this value right here. And I'm told that the coordinates of this hole are negative 3 and 7/6. We also have an asymptote at positive 3. This should be a minus 3 here. And 3, there we go. I also have a asymptote at positive 3. That's because of this factor in the denominator. This also creates a discontinuity at x equals positive 3, because if I put 3 in here, 3 minus 3 is 0. 0 times anything is 0. Anything divided by 0 is undefined. So I have another discontinuity. This one's an asymptote, though, because I can't cancel that discontinuity out. There's no way to get rid of it. So I draw an asymptote at that point. And these key features of this function and its graph we're going to see as we work with this function and look at its different limits. So that's kind of an introduction. And then in pre-calculus, there are some ways that we make some statements. Looking at this graph, we could read and find, as x approaches negative infinity, or as x goes to the left, the graph of the function approaches reads what? So if I trace this function toward the left, toward negative infinity, I approach this asymptote, which has a value of 2. That's how we wrote it in pre-calculus. We can look at the next one as x approaches positive infinity. And I head toward positive infinity, and the y value I approach, again, even though it doesn't look as close in this picture, this space here is a little bit greater maybe than the space here, but not by much, I can still see that the clear trend is that my function is heading toward this asymptote. And this asymptote also has a value of 2. As x approaches negative 3 from the left, so this is getting into maybe something a little bit more new. When I say from the left, that just means I need to start any place left of negative 3 and trace the function to see what does the graph of the function do. What y value does it approach? So here's my -3. I start someplace left of it and I trace toward, and I find I hit this hollow point, this discontinuity. And here's the key with limits. I do not care what the value of the function is. What I care about is what y value, what does the function approach? Whenever we think of limits, we should be thinking of approaching. What am I getting close to? What am I trending toward? I do not have to reach it. It doesn't have to exist, but it doesn't have to be defined. But am I approaching it? What is it that I'm approaching? So as I approach, as I head toward -3 from the left, I'm heading toward this point, which we determined was 7.6, the y value there. You can see this is just a little bit above 1 right here. Okay, so this one is 7.6. How about as I approach -3 from the right? So I head toward -3 from the right. Anywhere to the right of it, could be down here, could be here. If you start way over here, you're going to have to go up and then jump across this discontinuity and then continue to follow. So just to the right of it's fine. I start from the right and I head toward -3, which is here. And as I head toward it, I approach. Again, this is about 7.6 here, and I'm given that that's the exact value over there. Right down here. As I approach +3 from the left, here's my +3. It's this asymptote. And another set of words to kind of connect in your mind, and we'll see this more later, is that when I have an asymptote, I am dealing with infinity. And most of the times I'm dealing with infinity, I'm dealing with an asymptote. So we want to keep that in mind. I do have an asymptote here, and it's at 3, and I'm approaching 3. And as I approach 3 from the left, just from the left of it, and I go down, 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 down. What y value am I approaching? Well, I'm just falling without limit. I am approaching -infinity here off the bottom of the graph. What about when I approach 3 from the right? Here's 3. Here's the right. I head up, 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 up. What have we got? 5, 7, 8, 9, 10. I'm continuing to climb. I'm heading toward that asymptote. I am approaching +infinity. Okay. Now, these were how we phrased these in pre-calculus. In calculus, we have a bit of a shortcut notation. When I am saying as I approach, remember approach means limits, and limits means approach. So what we do is our shorthand is we write the limit as x approaches, we'll grab this, as x approaches -infinity of my function equals whatever that y value is. And this is my y value here, so this equals 2. This is my approach. This is my function. And remember, my approach is what is my x approaching. So I'm moving left and right. And then what I'm going to read off of that is what is my y value, or my limit. What is the value? What y value does my function approach? So if I do the same thing with my second limit here, I have the limit as x approaches. I always start with that. Here x is approaching infinity of the function, and this also equaled 2. This next one adds just a little extra twist. This has the from the right. When I have from the right, I start with my limit as x approaches. It's approaching -3. And from the left means from the left side of the graph. The left side of the graph is the negative side of the graph. So we indicate this with this little left superscript of the function equals and the value of the limit. So my little negative there meant from the left. My next question asks, as x approaches -3 from the right. So if approaching from the left means from the negative side, so I indicate with a negative subscript, what do you think I use to indicate that I'm approaching my limit from the right? I use a little positive superscript. Limit of f of x equals, and my value again was 7/6. My last two, as x approaches 3 from the left is from the negative side. So as x approaches 3 from the left, negative here, of the function equals -infinity. And the limit as x approaches 3 from the right, that's my little positive, of f of x equals +infinity. Based on what we've seen then, we can conclude that the limit as x approaches really any value, which I'm going to call a, this is some x value a, for a given function, is the y value that the graph approaches as x approaches a. So the limit is or equals, the limit is always going to equal a y value. So we look at the x value and we approach that x value, then we read the y value as our limit. All right, we're going to look at the same function, and we have the analytic function here, but how can we evaluate this numerically? What if I'm not familiar with the function and I still need to find the limit? So I have this function, and we're going to make use of our calculator. It has a function called table. Some models, I think the model that you use in class, table, you hit 5 for. This is a slightly different model, the 9860G, and you hit 7. But whichever one your table is, you look at table and press that number, and you're going to get a list of functions. And for our first function here, just as a demonstration, I want us to see how we will put this together. And the first thing we need to look at is, what will this function look like in calculator terms? And I want to notice that I'm going to be taking my numerator and dividing it by my denominator. So my numerator and denominator will need to set off in parentheses, and I can use the division between them. So in effect, I'm going to be putting into my calculator parentheses 2x, and I'll show you just which x to use. And then I'm going to use the x squared key in order to square the x, plus 5x minus 3, close parentheses so that everything in the numerator gets divided by the denominator x, the x squared button, minus 9, and then I'll close my parentheses and execute. Looking at my calculator then, I can just, as long as I have my function selected, I can start inputting that, parentheses, 2, and this is the x I want to use, not the letter x, that's the variable x, the letter x, I want to use the variable x, that's the x theta t, use my x here, squared plus 5x minus 3. Close my parentheses and divide by parentheses x squared minus 9. Close parentheses and execute. And that just saves that function in there. And what I want to do is view this in a table, and I can hit my table button here. These are soft keys, so whatever is up here, oops, didn't mean to touch it. No. Whatever is up here tells me my temporary functions for these f keys down here, f1 through f6. So table is F6. And this shows me my table. And I can take these values from the left, and I can just put all of them in my table. Oops. Negative 1,000. And it gives me the value. Go down to the next one and input negative 500. And gives me a value. And the next one, negative 100. And so on. Now, I'm just going to do the first ones here. For the rest of this lesson, I'll give you the values, because the important thing is that we be able to evaluate them. And later in another lesson, later in this unit, we'll talk about finding limits numerically where an asymptote's involved. So looking here, I see that my first set of values are 1.995, 1.99, 1.9514, and 1.9056. We'll go ahead and translate these over here. 1.995, 1.990, 1.951, 1.906. And the rest of our values, if we were to plug them into the calculator, okay, so this is what we see, and based on these values, we're asked first to find the limit as x approaches negative infinity. Now again, x is left and right, and to the left side is infinity, and way infinitely to the left is negative infinity. So that means I want to see what does this trend toward as we go left. And we started with some pretty big numbers here, so we're actually pretty close to the number we're approaching. If I were to have, and I could bring this up, if I were to have evaluated this for just, say, negative 5, I get 1.375. That's not quite so close. So I'd go 1.375, I'm going up to 1.906, 1.951, 1.990, and 1.995. I could try even more negative numbers, negative 5,000. And I would get 1.999. And what I'm looking for is what y value, that's my f of x here, what y value am I trending toward? What am I getting close to as my x value is approaching negative infinity? And I can conclude that I'm getting closer and closer and closer to 2. Now, depending on the calculator and how many zeros you put in, you might either get an error or get this value if you throw in a really big number, because the calculators aren't going to be able to be truly accurate with really, really large numbers like this with these functions. They may just go, nope, I don't have enough decimals for it. So we don't want to get so large that we're trying to actually touch it. In many cases, we can't touch the value. And the thing with limits is I don't care about touching the value. I care about identifying what am I trending toward, what am I approaching, what am I heading toward, what am I converging on. So looking at this, I see that I'm getting closer and closer and closer to 2. 1.999 is pretty darn close to 2. So I could conclude that the limit as x approaches negative infinity of this function is 2. Now this second function asks me, what about as I approach positive infinity? Well, positive infinity means heading off to the right. As I head off to the right, I look at my values. I start with 2.106, 2.052, that's a little lower, 2.01, that's getting pretty close to 2, 2.05 is very close to 2. I could try 5,000 and get 2. Oh, that was 500. 2.001, and I can conclude that this is growing closer and closer to the value of 2 as well, just from the other side. We're still looking at the same function now, but we're evaluating a different set of limits. Before we were looking at negative infinity and positive infinity. Now we're approaching -3 from the left and approaching -3 from the right. And I've gone ahead and filled in the values here. You should practice this with your calculator, but I don't want you to just sit there while I'm doing it, so you can try filling this in with your calculator and compare them to my answers. We're starting by approaching -3 from the left, remembering that this little negative up here, this means from the left. So I'm going to start left of -3. Well, where would -3 be? It would be right about here, between -3.001 and -2.999. And these numbers are chosen to get increasingly close to -3. -3.75, -3.1, -3.01, -3.001, -3.000001 would get closer and closer to -3, so that we can see that trend, what happens as I approach. Remember, limits, approaching, approaching, limits. So as I do this from the left, I am approaching from the left, and approaching as my x values get closer to -3 from the left. Looking at my values here, I see 1.259, 1.180, 1.168, 1.167. And this one's a little bit trickier than before. It's not heading toward an integer. But what's helpful to recognize here is you may remember your decimal equivalencies. 1.16 repeating, I'm sorry, 0.16. 0.16 repeating is the equivalent of 1/6. So 1.16 repeating is the equivalent of 1 1/6, or 7/6, which is what we found at the beginning of this lesson was the y value of the discontinuity. And if I approach from the right, I similarly see that I am approaching 1.167, 1.166. And so I can assume that this is also, I can conclude that this is also approximately 7/6. Go ahead and use your calculator to find the function values, or the y values, for this set of numbers. Same function from before. You shouldn't need to enter the function again, but you do need to input your numbers 2.75, 2.9, and so on. So here are our values, and we're finding limits this time as x approaches +3. And as I approach +3, again, this negative here means from the left. A little bit small there. As I'm approaching 3, +3 is going to be here. From the left, I'm getting very, very close. 2.999 is very close to 3. I look at the trend in my y values. I start with -18, -48, -498, -4,998. And what I'm finding is that I have some very big, very negative numbers. And as my numbers, as my x values get closer and closer to 3, I'll find that my y values will become larger and larger negative numbers. And if they continue to grow larger and larger and larger and larger, then they're going to approach -infinity. And generally speaking, in AP Calculus, if almost any time you're dealing with a number outside of a word problem, anytime you're dealing with a number outside of a word problem that's getting large, really larger than 100, you're probably dealing with an infinity type of situation, and you want to investigate that possibility. We do the same thing for our second limit, approaching from the right, or approaching from slightly larger values. 3.75 is larger than 3. 3.1 is larger than 3, but it's closer now. Same with 3.01 is even closer, and 3.001. And similarly, I go from 8.667 to 52 to 502 to even bigger, 5,002. And I see that my numbers are are becoming more and more positive, and they are going to infinitely grow. They're approaching positive infinity. So all of this leads us to the limit existence theorem. We've evaluated some different limits. We've looked at limits from the left and we've looked at limits from the right. But how can we find just a limit? Well, we have what's called a two-sided limit, or if we just say a limit and written such, the limit as x approaches a. This is called a two-sided limit because I haven't specified that it's a negative from the left. I haven't specified that it's a positive, meaning from the right. This is just the limit. And I like to use the word converges because it communicates the idea that for a limit, I need to be approaching from both sides, and both sides should be converging toward the same point for the limit to exist. And we're going to see that in the limit definition here. The limit of a function exists if and only if the limit as x approaches that same number, a, from the left of the function equals the limit as x approaches a, that number, from the right of the function. They need to equal each other, and they need to equal some number that is a real number. Now, we don't mean like agility. Okay, maybe that's not a real number, but that's not going to show up in calculus either. When we're talking about b being a real number as a condition, we're talking, really what we're doing is we're excluding infinity. Infinity is not a real number. To go more into that, take a different math class or do some research on your own. But infinity is not a real number. You can't actually reach infinity. You can't have an infinity. There are countable infinities and uncountable infinities, and it's a really fascinating topic that I encourage you to look into, but it is beyond the scope of this course. So the important part here is that b needs to be a number like 1 or 8 or radical 3 or a million or 0.00001, but it should be a number, not our little sideways 8 infinity. Infinity is not a real number, so a two-sided limit will never equal infinity. A left limit can approach infinity, and a right limit can approach infinity, but the actual two-sided limit can never equal infinity because infinity is not a real number. With that in mind, let's look at some specific examples of limits that do or do not exist. And I want to challenge you to pause and look at A, B, and C and evaluate these two limits. And the value of the function is just like what you've done in your previous classes. Where does the function exist? What is the function's value? Where it exists at, in this case, x equals 2. After you've paused and done that, go ahead and play and we'll check our answers. Okay, so as x approaches 2 from the left, here's my 2. I identify that. I approach it from someplace left of it, and I find I am going up. I'm approaching this asymptote. Asymptotes mean infinity. And in fact, I find I am going up. So the y value, I never really come close to a stop. My y value is increasing infinitely. I'm approaching positive infinity. For my x approaches 2 from the right, that's what my little positive here means. I start to the right of it, of 2, start to the right of 2 and approach it. And as I approach, I find I am similarly going up, and I am also heading toward positive infinity. C asks for the value at 2. And because this never touches my asymptote, my function from the left, and my function from the right never touches my asymptote, in fact, by definition, my asymptote can only exist where my function is undefined. And something to just pay attention to in calculus, we will talk about functions. A function can be undefined at a particular point, And a limit can fail to exist, and we typically abbreviate this does not exist. So, but we don't say that functions don't exist or that limits are undefined. We say that the function is undefined and that the limit does not exist. So for C, we say the function is undefined. For D, it asks, does the limit, this is a two-sided limit, as x approaches 2 exist? Or does it not? And why? So remembering my two steps to check for a limit existence, does the left limit, little shorthand here, equal the right limit? That's my first check. Does my left limit equal my right limit? Well, yes, infinity equals infinity. My second check is, does the number they equal, is that real? Is that a real number? And we've said infinity is not a real number, so this limit does not exist. I would write this out, the limit as x approaches. I would write this out, although the limit as x approaches 2 from the left equals the limit as x approaches 2 from the right, the function. The limit does not exist. The two-sided limit does not exist because it is not a real number. And I would write that out. We never use pronouns. The limit as x approaches 2 is not a real number. We don't use pronouns, we write things out. Okay, number 2, go ahead and pause and try to find A, B, and C. All right, our limit as x approaches 2, here is 2. From the left, I start to the left and I head toward 2, and I find that as I get close to x equals 2, my y value is getting pretty close to 2. So there's my 2. And same thing as I approach 2 from the right, here is right of 2, and I approach and I find that I'm also heading toward this y value of 2. Now, for the value of my function, that's where does my function exist at 2? Where is it solid? It's not solid here. This hollow means it does not exist here. That is an undefined point. But I do find that my function is defined down here with the solid dot. And this dot's value is -3. So the value of my function is -3. Now, does my two-sided limit as x approaches 2 exist? Well, let's check the steps. Does my left limit from the left equal my right limit? Does 2 equal 2? Yes, I have passed that step of my limit existence theorem. The second part is, do they equal a real number? Well, is 2 a real number? 2 is a real number, so this limit does exist. The limit as x approaches 2 of the function exists because the limit as x approaches 2 from the left equals the limit as x approaches 2 from the right equals 2, and 2 is a real number. Our final example before we start part 2. Our final example is example number 3. Go ahead and try A, B, and C, and then try D. See if you can determine whether this limit exists, and when you're finished, unpause the video. All right, so my limit as x approaches, this is +2 from the left Here's my positive 2. I start someplace left of it, and I head toward 2, and as I get close to 2, I find that the y value that I'm getting close to is 3. For b, I'm still approaching positive 2, but this time from the right. It's a little difficult to tell, but that's a positive sign. Here I'm approaching it from the right. Here's my 2. Someplace to the right of it, I head toward 2, and I find that the y value I'm approaching is about negative 3. How about the value of my function? Looking at 2, I look straight up and down and see where does this function exist. It's undefined here at y equals negative 3, but it is defined here at y equals positive 3. So the value of my function is 3. Now for d, does my limit, my two-sided limit as x approaches 2 of f of x exist? And why or why not? So we want to check the two steps. First, does my left limit, well, we'll use 2 instead of a, does my left limit equal my right limit? From the left and from the right. And looking here, I have my left limit is 3, and my right limit is negative 3. And those do not equal each other. So since, or because, the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x, the two-sided limit, the limit as x approaches 2 of the function, does not exist. And that's it for this lesson. You can pick up with 1.1b.